All right, ever try to open one of those super stubborn pickle jars? You're twisting and turning, and it's like those pickles are glued in there. Well, that, my friend, is what we're diving into today. The surprisingly stubborn world of force and motion. We're using excerpts from this super interesting science textbook chapter as our guide. To unpack Newton's laws of motion, the rules that dictate why that pickle jar is mocking your biceps, and basically how anything moves anywhere, ever.
It's true, those laws are everywhere.
But before we get to the rock star of physics, Sir Isaac Newton, let's rewind a bit. Imagine, if you will, it's the days before Galileo, before telescopes and fancy experiments. People looked around and thought, okay, things are usually just chilling, right? Like roll a ball, it eventually stops. Seems logical, yeah.
Absolutely. It makes perfect sense if you're just going off of what you see every day. Ball wants to be at rest, just like that stubborn pickle jar lid. But that's where things get interesting. It took some seriously clever minds to realize that our intuition isn't always the best guide, especially in the world of physics. For example, did you know that people used to think heavier objects fell faster than lighter ones?
Really?
It seems obvious, right? A bowling ball would totally beat a feather in a race to the ground. But turns out gravity affects everything equally. It took meticulously designed experiments to finally put that misconception to rest.
See, that's what I love about physics. It's full of these aha moments where what we think we know gets flipped on its head. Okay, so speaking of things that are heavier than they look, let's unpack this idea of force. The textbook defines it as anything that has the potential to change an object's state of motion. But what does that actually mean?
Good point. It's easy to get lost in the textbook jargon. Think of it this way. Force is anything that can make something speed up, slow down, or change direction. Basically, any push or pull that messes with an object's groove.
Okay, so our pickle jar, stuck in its stubborn stillness, is definitely feeling some kind of force, right?
Exactly. You're applying force to twist it open. But there's also force working against you. The friction of the lid, the tightness of the seal, maybe even a bit of air pressure inside. It's a real physics showdown happening right there on your countertop.
And to think, I thought it was just me versus snack craving. So force is about changing how things are moving. But the textbook also says it can change an object's shape.
It can. Think about pressing your hand into a big lump of clay. You're applying force, and you can see the clay change shape right before your eyes. Or picture a potter molding a lump of clay on a wheel. The force of their hands transforms that shapeless blob into something beautiful.
Okay, that's actually really cool. So it's not just about moving, it's about changing. Like that car speeding off from a stoplight force. Or, hey, even a gentle breeze rustling the leaves on a tree. That's the wind's force in action, right?
Yeah.
You're talking everything from subtle nudges to powerful shoves.
You got it. Force is everywhere. And this brings us to the first of Newton's brilliant insights, the law of inertia. You know that stubborn streak that objects have? They like to keep doing what they're already doing. Yeah, they like to just keep on keeping on. Imagine you've got a magical frictionless bowling ball.
Okay, frictionless bowling ball.
You roll it down the lane, and guess what? It just keeps going and going and going forever.
Forever.
Of course, back here in the real world, we've got things like friction that eventually bring things to a screeching halt.
Which explains that feeling we were talking about earlier, that jolt when a car slams on the brakes. Your body's just trying to keep rocking that straight-ahead motion thanks to inertia. But your seatbelt gently reminds you, nope, party's over, time to stop.
And you know what's really cool? This whole idea of inertia. It's not just some abstract physics concept. It's why we wear seatbelts. It's how airbags work. It's even a key player in designing those awesome roller coasters that send you flying through loops and drops.
You're right, inertia is a pretty big deal. But speaking of big deals, let's talk about changing an object's motion, not just keeping it stuck in its ways. And that's where Newton's second law comes in, which is all about the relationship between force, mass, and acceleration.
Okay, time for a confession. This is the one that always made my eyes glaze over a little bit back in school. Can you give us the non-textbook version?
Absolutely. Imagine you're playing a game of ping pong.
Okay.
You flick the ball with your wrist and it zips across the table. Now, picture trying to move a bowling ball with the same flick of your wrist.
Yeah,
What's going to happen, right? Right.
That's because the bowling ball has way more mass, so you need a lot more force to make it move with the same acceleration as that little ping pong ball.
So even if they're both moving at the same speed, the bowling ball has more of that, like, oomph factor because it's got more mass.
You got it. And that oomph factor, physicists have a fancy name for it. Momentum. It's basically the measure of how much motion an object has. And it depends on both its mass and its velocity. The heavier and faster something is, the more momentum it's packing.
Okay, I'm starting to see how this all connects. So more force means a bigger change in momentum, and heavier objects need a proportionally larger force to get them moving. It's all about how much oomph we're talking about.
Exactly. And just like with inertia, Newton's second law is working behind the scenes in countless ways. It's the reason why a small car gets better gas mileage than a big SUV.
Oh, really?
Yeah, it takes less force to get that smaller mass moving, and it's why you need a super powerful engine to launch a rocket into space. You're dealing with a massive object that needs a whole lot of force to overcome Earth's gravity.
Wow. So from fuel efficiency to space exploration, it's all connected to this one law. This is why I love the deep dive. It's like suddenly you're seeing the Matrix, but for physics.
Yeah.
Okay, so we've covered objects at rest, objects in motion, and how much oomph they have. What other mysteries of the universe did Newton unravel?
Get ready for this one because it's a classic. Newton's third law, the one everyone knows even if they've never cracked open a physics book.
Okay.
Ready? For every action, there is an equal and opposite reaction.
Okay, on the surface, that sounds almost too simple. Like, yeah, of course, if I push on something, it pushes back. What's so groundbreaking about that?
It seems deceptively simple, but here's where it gets really cool. These forces, the action and reaction, they don't act on the same object. It's like a physics tango.
Well,
Always paired, always opposed, but on different dance partners.
okay, I'm intrigued. Give me an example.
Picture this. You're at the firing range, and you pull the trigger of a rifle.
Okay.
The bullet explodes out of the barrel with a powerful force, right? Well, that's the action. And what's the equal and opposite reaction? The gun recoiling back into your shoulder with an equal amount of force.
Oh, wow, yeah. I never thought about it like that. But it makes total sense. The bullet goes forward, the gun kicks back.
Precisely. And the reason the recoil doesn't send you flying backward is because of mass. The gun is much heavier than the bullet, so even though the forces are equal, the gun's acceleration is much smaller.
Okay, so it's not just an empty phrase. It's this whole intricate dance of forces happening all around us. Speaking of dances, and this might sound silly, but I'm reminded of that time I tried to jump off a little raft in the lake, thinking I could just, defy physics and float through the air. Instead, the raft shot back in one direction, and I landed with a very ungraceful splash in the other. Classic Newton's third law fail.
It happens to the best of us, but you're right, it's the perfect example. You push off the raft, action, and the raft pushed back on you with an equal and opposite force, reaction, sending you both in opposite directions.
So we've got these three seemingly simple laws, but I'm guessing they're about to unlock some serious aha moments about the world around us. It's like Newton gave us the cheat codes to the universe.
Yeah.
Okay, so we've got these three laws, and they're not just about marbles on ramps for firing ranges. Remember that pickle jar we started with? Total example of Newton's first law. Your Herculean effort to overcome that jar's inertia.
Exactly. And that car we talked about earlier, zooming away from the stoplight, that's Newton's second law in action. The
Right.
engine's force, the car's mass, all coming together to create that satisfying acceleration.
And you know what really drives it home for me? Think about that gentle breeze rustling the leaves on a tree. It seems so simple, but it's actually this elegant dance of forces described by Newton's third law. The wind pushes on the leaves,
Yeah.
the leaves push back on the wind, and voila, we've got ourselves a little symphony of motion.
What's even more mind-blowing is that these laws, figured out centuries ago, are still the bedrock of pretty much everything we do in our modern world. Think about it. Airplanes staying aloft, bridges standing strong against gravity.
Yeah.
Even just designing a more efficient wind turbine, it all comes back to understanding force and motion.
It makes you appreciate the power of a truly groundbreaking idea. Newton basically cracked the code of movement.
He did. And speaking of cracking codes, I think it's time we leave our listeners with something to ponder. We've explored these fundamental laws, but the true aha moment comes when you start applying them to your own world.
Okay, I love where this is going. Give us that final mind-expanding thought.
Here's a challenge for you. How could you use your newfound knowledge of force and motion to create something new? Maybe it's a gadget that utilizes these principles in a surprising way, or perhaps a thought experiment about the immense forces at play in something like, launching a spacecraft to Mars.
See, this is why I love physics. It's not just equations and formulas. It's a whole new way of looking at the universe and the incredible forces that shape our everyday experiences. Who knows, maybe your next aha moment could lead to a groundbreaking invention or a mind-bending scientific discovery. So keep those physics fires burning, my friend, and if this deep dive sparked any aha moments for you, we'd love to hear about them. Until next time, keep exploring and keep asking those big universe-unraveling questions.